I'm Emily.
Hi, I'm Isabella.
Hi, I'm Anna.
Hi, I'm Iris, and this is our Newton's Laws project.
Newton's first law, also known as the law of inertia, states that an object in motion will stay in motion and an object at rest will remain at rest unless acted upon by an unbalanced force.
For our first demonstration for Newton's first law, we see a ball starting at rest being rolled by a force applied. The ball kept rolling and only it stopped until an unbalanced force acted upon it. And this is a good way to prove Newton's first law.
This demonstration proves the concept of inertia. Inertia is the tendency of an object at rest to remain at rest unless the force acts on the object to move. The coin has inertia, which makes it want to stay in one place. When you flick the card quickly, the coin stays in the same place. The coin stays in place because the force pulling the card isn't enough to make it move.
Second law. Newton's second law is when the acceleration of an object is directly proportional to the net force applied and inversely proportional to the object's mass.
Go.
First demonstration for Newton's second law, we see a water bottle that is half full being rolled down an incline a certain distance. It takes that water bottle about 4.30 seconds to be rolled down that certain distance because of the force applied that is also equal to its mass and its acceleration. Then we see another water bottle being rolled down that same incline, but this time the bottle is full, and therefore it rolls faster because the mass is greater than the first bottle. Therefore, also its acceleration will be greater because of the mass being greater. This is due to the fact that Newton's second law states that force equals mass times acceleration.
One guy was training, so it was the two guys and then the guy training.
Second demonstration for Newton's second law, we see an empty cart being pushed down a certain distance, and it takes about 7 seconds for it to be pushed down with a certain force. Then we see a full and heavier cart being pushed down that same distance with that same force as the first one. And we can see how it takes longer to push that cart down because of its heavier mass. Also, its acceleration will be slower than the first one, again due to the fact that F equals ma, force equals mass times acceleration. It just states that if it's heavier mass, then we're going to have a heavier force and a less acceleration.
Newton's third law is the interaction between two objects. So when one object exerts a force on a second object, the second object exerts an equal force in the opposite direction on the first object.
First demonstration for Newton's third law, we can see Emily swimming. As she is trying to move in one direction, she has to do a motion opposite to the direction she wants to move in with her arms in order to be able to swim. This proves Newton's third law because in order for Emily to swim, a motion in the opposite direction of her motion must be done, representing the interaction between the water and herself. For a second example for Newton's third law, we see Emily swimming again, but this time she's pushing herself off the wall of the pool in order to be able to go in a different direction that she's swimming in. When she spins and touches the wall, she's applying a force into the wall, and then the wall applies a force back on her that propels her in the direction that she wants to go in. With this example, it is evident that Newton's third law is accurate because there is an interaction between two objects, and then both objects propel a force that is opposite in direction but equal in magnitude.